Hi, my name is Cody Deacons, and this is a presentation on Lab 4 digital sampling for AE2610. So digital sampling is any time that you're measuring a time variable function with a digital device. It's used in tons of real-world applications. Anytime that you're measuring something that's varying with time, that is a function of time, and you're using a digital device, there's some specific ramifications that come with that. In our upcoming experiments that you'll see, we focused on the sine wave formed from an audio signal. It's just one of the most common and analyzed signals that you can see. So the objectives of this were to explore methods to measure these using a digital acquisition device, compare the relative response of a particular microphone to audio signals, because that could give us some insight into basically how that compares with reading that signal directly, and we'll see that later. As well as design and perform our own experiment to investigate properties of sound or the data acquisition itself, because we can learn a bit about both from that. So for our first experiment, the equipment was a LabJack T4, data acquisition device, a small generic microphone that plugs into it, a frequency sound generator app that I just got off the App Store, as well as some DAC software that was developed by the AE department here at Georgia Tech. So our approach was initially to measure the power outputs for multiple signal frequencies directly with the data acquisition device. And then we did the same thing, but with a microphone, with the same power and everything in theory. That way we can compare the relative power levels between them at separate frequencies, and you can see the equation for relative response over on the right. You're basically just comparing the voltage that your microphone gives you by the direct reading from your data acquisition device, so you can get from a direct connection. So on the right here, you're seeing a plot of relative response against frequency for our experiment. Initially, we took 10 different data points for this. However, the first 4 were impossible to tell because the microphone power spectrum had a large spike at really low frequencies. I'm not really sure why this was, but it meant that we couldn't get a value for relative response for those first 4 data points that I took. As you can see, it trends downward as frequency increases. This leads me to think that the microphone has a circuit element known as a low pass filter, which lets basically lower frequencies through and attenuates or cancels out the higher frequencies as it goes on. I noticed something really weird when I was doing this, specifically in the time histories of the top 3 data points. So you'll see at the top, this is the 7500 hertz. In theory, all of these are supposed to be just a normal sine wave. At least that's what my function generator app was telling me. However, you can see the top, that looks a lot more like what you would get when you sum 2 different sine waves in a graph. The middle, the 9000, there's something weird going on. It's really hard to tell. The 10,000 actually looks like what happens when you multiply 2 sine waves together. You'll also notice that the peaks are very sharp and straight, and that's because of the amount of data points that the digital sampling is taking. I tried to turn this up, however, it crashed the program every time, which leads me to think that we were hitting the top end of the number of samples per second that our data acquisition software could actually hit. So for my experiment, I thought about how sound power or volume lowers over a distance. I was wondering if the microphone could pick that up on a very small scale, specifically a foot. As you can see, I'm using a ruler right here. So I picked 2 different frequencies and measured the amplitude over a bunch of distance increments, 1 centimeter each, while keeping my phone volume measurement set up and the microphone orientation to my phone the same. So as you can see here, here are 2 plots of the voltage, the power, and the distance for the 3000 and 9000 hertz, as well as lines of best fit. And we're going to see how those compare here on the next slide, but you can see that our R2 values are pretty decent, better for the 9000 though. So those lines of best fit did generally fit the expected proportionality rule for the power of a sound wave over a distance, and that's that power is inversely proportional to the square of the distance. In our lines, our exponents were -1, which is a bit off, but I think that that error came from the acoustic resonance or something, creating constructive interference, since there's a solid table right beneath the phone that could be reflecting sound waves. So the big lessons learned from these experiments is that your instrumentation can manipulate your data like we saw with the microphone and its potential low-pass filter, as well as the data acquisition device and its limits on sampling rate. You also need to choose an appropriate sampling rate and consider what error you're going to get when you digitize your data, because there are limits on what your data acquisition software and hardware can do for you. Thank you.